my dear student, I'm Saktwala from Educare TZ. I will be with you in physics for Form 5. And today, my dear student, we are going to proceed with our discussion here on our topic of a circular motion, simple harmonic motion, and the gravitation. Now, let us continue with our subtopic of the gravitations. As we have tried to look on the last session, we said that the gravitation should it act between two objects or two bodies which contain their masses, and they also they are split apart from each other. So, my dear student, today we will go and look on the gravitation due to gravity. How can we define the gravitation due to gravity? How can we derive the formula of the gravitation due to gravity related with the gravitational force or the gravitational pull? So once you observe here that we have consider an object of mass m. Now we have the object that contains the mass m, and it is placed on a uniform spherical SC of mass m. This implies the mass of the S. But the radius and the radius L, as it shown on the figure number 3.34. Now we are going to see the mass. We are going to see the spherical, and that spherical containing the mass m. But that mass m is placed on the spherical, and that spherical containing the S, the mass of the S, and also the radius of the S. Now, how can we derive the gravitational force? The gravitational due to the gravity are related with the mass of the S. How can we demonstrate? So once we observe our figure here, this is the figure that represents a body placed on the surface of the S. Now we have our figure here, and as you can observe that on our figure here containing the spherical, we have the surface of the S. That is the surface of the S as we try to observe here. But this mass m is placed on the spherical. It means tried to move around to the S. This is in an orbit, as we try to see. We have an object of mass m, and that object try to move around the mass, around the Earth. But when it moves, it try to give us, it form the radius of the S. It means from the center of the S up to the point where the mass is originated there, now give us the distance of the S that we call as the radius of the S. And this always is the same, kwamba even if when an object reach at this point, the radius of the S will be the same. Even if it will be at the left side here. This implies that the radius of the S will be similar. At the center here, we have the mass of the S. Now we have the S at the center. That have its own mass. Now that object tried to move around the mass of the S. Once we try to observe here. So the gravitational force of attraction on mass m, the gravitational force of attraction on mass m is obtained from the Newton law of gravitation. How can we obtain the gravitational force of attraction of mass m? So the gravitational of attraction of mass m is obtained from the Newton law of the gravitation. The Newton law of the gravitation, which states that the force of attraction in the universe, between two masses in the universe, or between two bodies on the universe, is directly proportional to the product of their masses and the inversely proportional to the square of their distance. As we try to observe here, that the law say that the force of attraction that is exerted between the mass m and also the mass of the s is inversely proportional, is direct proportion to the product of their masses. This means that it is direct proportion to the mass m and also to the mass of the s's, but inversely proportional to the radius of the s. That is how we can start the law of the gravitation, the Newton law of gravitation. So from the Newton law of gravitation, as we tried to recall that how can we state that law? Now we should obtain that the force of attraction, when we reduce the direct proportion, it must be equal to the g, this g, universal gravitational constant, times the mass of the s, then we times it by the mass of an object, then we divide it by the radius of the s. That is how we can introduce the force of attraction. It means kwamba tutachukua force of attraction ambao ana exert hapa should be equal to the g. This g means the gravitational constant times the mass of an object, then we times it by the mass of the s, and after there we try to divide it by the radius of the s. So this should be our formula of obtaining the force of gravitation. But after there here, now let us imagine that because here this object here, my dear students, form the downward force which is equal to weight. Now we should say that the force of gravitation that exerts between the mass of an object and also the s, the mass of the s, then we divide by the radius of the s, should be equal to the weight or the downward force, which is equal to mass times the accelerations. So the attraction force which the AC exerts on an object is the weight of an object, as I tried to explain that. Because that is on the center, should provide the downward force or the force of attraction, which is called the weight. Now we should say that this force must be equal to the mass times the acceleration due to gravity, which must be equal to the gravitational universal gravitational constant. We multiply by the mass, this mass of the s, then we multiply by the mass of an object. We divide it by the radius of the s. So therefore, here, because we have two equations, we have mg is equal to gme, m divided by ra square. Now, as we observe here that this mass of an object is common, and if it is common, now we are supposed to cancel each other. We should omit this mass because it is found on both sides. Now, if we will cancel here, we should observe that, we should obtain that the gravitation of the acceleration due to gravity of the s must be equal to the gma divided by ra. But this g implies the acceleration due to gravity of the s. But g here should stand instead of the universal gravitational constant. But ma should imply the mass of the s, where ra should be the radius of the s. Now we obtain the acceleration due to gravity of the s, which is equal to the universal acceleration due to gravity. Then we multiply it by the mass of the s, and after there we divide it by the radius of the s square. So this should be the equation number 3.47. The equation that we tried to see. Instead, we started our topic here up to now. This is the question. The question number 47 on the topic number 3. So, my dear student, after there, the mass of the AC can be calculated from equation 3.47. Now we should calculate the mass of the S using our equation number 3.49. How can we calculate the mass of the S? Now, if we want to calculate the mass of the S, first of all, let us know that, as we know that the acceleration of the S here is constant. If we substitute the universal gravitational constant, which is always constant, and the mass of the S, which is always constant, the radius of the S, now we should get the acceleration of the acceleration due to gravity of the S. But if we want to obtain the mass of the S here, we are supposed to use our equation here so as to obtain it. So how can we get the mass of the S? And we have been told that to use this equation number 3.47. Now we have to make this mass of the S as the subject, because we are supposed to use our equation here and obtain the mass of the S, the formula of obtaining the mass of the S. Now we should multiply by Ri square both side, by Ri square both side. Now we will get, and after multiplying, we are supposed to divide it by the mass of the S. By the universal gravitational constant. If we divide it, we should obtain that the mass of the Earth, my dear student, should be equals to GRE square divided by GRE square divided by the capital letter Ig. But the small the least Ig here represented the acceleration due to gravity, while the Re represented the radius of the S, the radius of the S. But the G here, the capital letter G, should represent the universal gravitational constant. So after there, my dear student, this will be our equation number 3.49. Going into equation number 48, it means on the topic number 3. So, and the density of the S. Now, let us try to see that how can we get the density of the S here. The density of the S, my dear student, is obtained by using this equation. We should use the equation number 48 on our topic number 3 here to derive the formula of obtaining the density of the S. Now, we should define the definition of the mass or the density of the S. As we know that the density must be equal to the mass per unit volume, the way we have been taught when we was in Form 1 on the topic of density and the relative density. That we obtain the density of the S by taking the mass divided by the volume. But here we are talking about the S. It means the density of the S must be equals to the mass of the S. Then we divide it by the volume of the S. So after that, my dear student, we should substitute our given values. Because here at above we have the mass of the S, and on our formula here we have the mass of the S. Now we are supposed to take this formula here and put it here at the point, at the place where there is the mass of the S. Then the volume of the S should be equals to 4 pi r cube. 4 pi r cube of the S. It means tunapata ile mass of volume of the S kwa kuchukua formula ya volume ambayo ni 4 pi r cube, kwa sababu tunaongelea kwenye sphere. If we are talking on the sphere, kwa volume of the S must be equal to 4/3 pi r cube. This r implies the radius of the S. So if we substitute here, we should get that the mass, we should obtain that the density of the S must be equal to GRA. It means the acceleration due to gravity times the radius of the S. Then we divide it by the gravitational, the universal gravitational constant. We multiply by 3/4 pi r cube. This is the formula of obtaining the volume, because the 3 was at below here. Now if it was below, kama ilikuwa iko chini na tena chini, it means we are supposed to take it and put it above, kama tunavyoona hapo. So my dear student, since the AC is sphere, therefore, now because we know that the AC is sphere, my dear student, now the density of the AC must be equals to 3G. As you can observe here, at the top we have the radius of the A square, but at downward here we have the radius of the AC cube. Now we should cancel the power 2, or you can use it the law of the exponents, that on division. If we have the same base, we are supposed to take it the exponents and the minus. So if you minus, you will obtain that the density of the AC must be equal to 3G. Then it divided by 4RE times the universal gravitational constant. So equation, this will be our equation number 3.49. Hii itakuwa ni equation yetu ya 49 on our topic number 3. So usichanganyikiwe sana kuhusu formula kwamba zimeshafika ni nyingi. Ni amna. The thing that you are supposed to consider to know, usiclaim, you have to know that how can we get the density of the AC. Ukiachana na hii equation, formula yake lazima iweze kukaa kichwani kwa kusolve maswali mengi. Ukisolve maswali mengi, hapo ndo formula itaweza kukaa kichwani. Lakini ukiwa unaiangalia tu alafu unakalini 3 na number 49, hapa haitakusaidia. The thing that should help you is to know the formula. How can you use the formula of obtaining the density of the AC? So my dear student, equation number 3.47 provide the value of G on the AC surface. As we have tried to say that that equation number 3.47 give us the value of G on the S on the surface of the S. So after there, experiments show that G varies from the place to place on the surface of the S. Kwa hizo equation, hizo experiment ndo zinakuwa zina imply kuwa huyu G anakuwa ana vary from the place to place on the S. Kwa that G should vary from place to place of the S as well as the attitude. So let us go and see the variation of G with attitude, because here we are going to see the factor that should affect the acceleration due to gravity. One of them is the attitude. And we try to say that how the attitude should affect the acceleration due to gravity of the S. Once the attitude increases, my dear student, this should cause the acceleration due to gravity to be changed, to be increased. So how? Consider our figure here, and this figure have the mass m, as we have tried to see on our figure number 3.34. Now let us look for our figure number 3.35 here. That firstly we have tried to see that this mass of an object was at the spherical, was in an orbit. Now let us imagine that that is above of the spherical of the S. Kwa inapokuwa ipo juu, it means we should have it should act at the certain height. This is an attitude from the spherical sphere. But here, from the spherical sphere up to the center, this implies the radius of the S. But here, above here, my dear student, here up to the center point where it is allocated the mass of an object m, should be the radius. This radius, we obtain it by taking the radius of the S, then we add it by the attitude or the height. So after there, if we recall our formula, we should obtain that this acceleration due to gravity at a certain point P, here, should be represented by G dash, as we can observe here. G dash must be equal to universal gravitational constant. If we multiply by the mass of the S, then we divide it by R square, as we try to see. but this r is the distance from the center up to the mass, where the mass is allocated at an attitude, at a certain an attitude there. So this will be our equation number 3.50. Kwa hii ndio itakuwa equation yetu ya g dash. It means kwamba at a certain point, at point P, it means at a certain height. Kwa itakuwa g dash is equal to gme r square. So here, my dear student, if we make a comparison with our equation number 3.47 here, we should obtain that g dash should be equal to GRE, kwa sababu should be equal to GRE square divided by r square, r kubwa square, ambao ni above a certain point. How this is obtained? Tumechukua ile ya kwanza, equation ya kwanza, tukamake mass of the s at the subject, na baada hapo tukaja tukasubstitute kwenye hii equation yetu hapa palipo na mass of the s, tukapata equation yetu hii hapa, na hii ina imply kuwa always the acceleration due to gravity at a certain point is inversely proportional to their attitude, to the distance. It means to the distance from the center of the body up to the from the center of the body to a certain point. So since GRE is constant, now this will be the end of our session, my dear student. Now I would like to welcome you again for another session. I wish you all the best. Have a nice moment.